firstly, we learned about this Coulomb's law, right? So I will keep revising again and again so that you guys don't forget anytime soon, right? So firstly, we learned about this Coulomb's law, right? That we have this force which is K Q1 Q2 by R squared, right? And then we added this Coulomb's law with mechanics. So we added with mechanics, and in mechanics part, we learned about this spring, or let's say tension. Then we learned about this spring. And then we learned about this simple harmonic motion also, right? So this we did in the Coulomb's law. So this was again added with this equilibrium. Right, guys?
Yes, yes, sir.
And we also learned the superposition principle of charges, right? So we calculated the total force as F1 plus F2 plus F3 plus so on. So this we learned. And then what did we learn? Then we learned about this vector form of Coulomb's law. So in vector form, we learned that you can write F1, 2 as K, Q1, Q2, R1 minus R2 divided by R1 minus R2 power square or cube, Rabia? Yes. Square or cube, Rabia? Forgotten? Aisha?
Cube.
Cube. Yeah, cube is the right answer. If I have vector in the numerator, so there would be cube. Yes, right answer. Okay, and then we learned about the electric field. Right. Electric field due to point charge. And then we learned about this superposition principle. Okay, and then we learned about this electric dipole. Right, electric dipole, which was, this was electric dipole, and the dipole moment direction was this, right? And the magnitude of the dipole moment was charge into separation. Right, and after that, we learned about, the electric field due to dipole. So in the electric field due to dipole, we learned about two positions, right? So this was the dipole moment direction, and first we calculated the electric field at this line. So what is this point called, Aisha?
Axial point.
Axial point. Absolutely correct. So electric field at the axial point we calculated, and this was in the direction of the dipole. And then we calculated the electric field at the bisector of this point. So what was this point, Rabia?
Equatorial.
equatorial point, right? So E equatorial. And what was the direction of the equatorial electric field? Yes, Rabia. Yes, forgotten. So this was in the opposite direction of the dipole moment. Right? Is that correct, Aisha?
Yes, sir.
Yeah. So E axial was how much? This was how much, Aisha?
2 kb by r square
2 kp by r square?
cube.
Q. Yes, yes, r cube. And what was E equatorial, Rabia? Yes. What was E equatorial, Rabia? Revise, Rabia. Revise, revision. Okay, so this was minus Kp by R cube. Do you remember now, Rabia?
Yes, I knew it, but I wasn't sure.
Yeah, so you can see it from here that this is against the direction of this dipole moment vector. So these were the two electric fields that we calculated. And in the next part, we learned about force on charge particle in external electric field. Right. So before that, we learned about this electric field lines. Right. And after that, we learned about this force, and we learned that if this is the direction of the electric field, so if I put some charge in here, so this will experience, this is positive charge, so this will experience force in this direction, QE. And if I put some negative charge in here, so this will experience the force in the opposite direction, which is minus Q. And then we learned that what is the torque on electric dipole in electric. So we have this electric field, right? We have this electric field, and then we place some dipole. So this is the direction of the dipole moment, right? So the torque is equal to how much, Aisha?
P
Yes,
cross E sine
P
theta.
cross E. Yeah. So if you are telling P cross E, so this would be simply P cross E. And if you are writing the magnitude, so this would be P E sine theta. Right. And then we learned that we have three cases, three special cases. So in first case, theta was 90. So torque was maximum. And in the second case, theta was 0. So we had stable equilibrium. Right. And in the third case, theta was 180. So this was unstable equilibrium. Right. And after this, we have this new topic, which is electric flux. So in today's class, I'll be doing some questions on electric flux and Gauss law. Okay, so electric flux simply tells that whatever So we have this surface area, right? We have this surface, and whatever amount of electric field lines is passing through that area. So let's say that 1, 2, 3, 4, 5. So 5 electric field lines are crossing. So the electric field line, this would be 5. Right. So whatever number of electric field lines passing through an area which is perpendicular, right, to the surface. So this is called the electric flux. And this is represented by electric field dot the area, right? Right, guys. So this much you guys know. Right.
Yes, sir.
Yes, sir.
And if I calculate the flux of a closed surface, if I calculate the flux of a closed surface and it has some charge Q, so the flux would be simply Q enclosed or Q inside by epsilon naught, right, which is Q by epsilon. In this case, this would be simply Q. Right. And this doesn't depend upon shape. So whatever is the shape, the flux would simply be Q by epsilon. Whatever is the shape. Right. So this is about the flux law, and this is called the Gauss law. Right. This is called the Gauss law. For a closed surface, my flux is Q by epsilon naught. So this is called the Gauss. Is that clear, guys?
Yes, sir.
Yes, sir.
So my flux in closed surface is represented by this. So this is Q inside by epsilon naught. So this is the integral form of Gauss law. Right. So this much you guys know already. Okay. Yeah. So Rabia, you know this much already, right? This you have learned
Yes, sir.
in your Amna ma'am class. Yeah. So using the Gauss law, we calculated the electric field of 3 systems. So firstly, we calculated the electric field of a line charge. So this we calculated to be how much? Yeah, infinitely long wire. So what is the electric field of this infinitely long wire, Rabia?
Lambda by 2 pi epsilon naught r.
Yes, absolutely correct. So this is lambda by 2 pi epsilon naught r. And we have the second distribution, which is this sheet. Okay, so we have this sheet, and this has some surface charge distribution sigma. So what is the electric field of this sheet, Aisha?
Sigma by 2 epsilon.
Yeah, sigma by 2 epsilon. Yes, so you guys remember it correctly. And for the case of the fourth one, we have this hollow sphere, right? So for the case of the hollow sphere in the outside, we have E inside is how much, Rabia? For the case of hollow sphere, E inside is how much?
Yes.
Yes, Rabia. Yeah.
Sir, I don't remember.
Ah, you don't remember. So you see that what is the charge inside this sphere? Do you have any charge inside the sphere?
No.
Yes, Rabia. So do you
We
have
don't
any
have.
charge inside the sphere?
No.
Yeah. So if there is no charge, so the electric field will be how much? 0, right? And
Yes.
E outside would be simply KQ by R square. Okay, so this behaves like a hollow. This behaves like a point charge. Is that correct, Aisha? Yes.
Could you repeat?
So this is yeah. So this is yes, Aisha. What did you say?
Could you repeat?
Yeah. So E outside due to this hollow sphere would be how much? This is this, right?
Yeah.
Yeah. And this is exactly like a point charge. So this outside field behaves like a point charge. This sphere behaves like a point charge, right? So this I was telling. Okay, now the concept part is done. So let us do some problems. Okay, so the first question. And in today's class, this chapter will be over. So we would complete this chapter and then we'll move on to this second chapter. So what is Amna ma'am doing in your class, Rabia? Electric current?
Yes, sir.
Yeah, so then we'll start this electrostatic potential in the next class. Okay, our sphere encloses an electric dipole with charge plus minus. What is the total electric flux across the sphere? And this has been asked in 2019. So we have a sphere, right? And an electric dipole is placed. So this is minus Q plus Q, right? And what is the total electric flux across the sphere? So flux would be how much? So this is a closed sphere. So what would be the electric flux, Rabia? Yes, Rabia.
Q by epsilon naught.
Q by?
Epsilon naught.
Yeah, Q enclosed by epsilon. And how much is the total charge Q, which is enclosed? Let me write it as Q inside. So how much is the charge inside of this sphere? Rabia. How much is the total charge inside that sphere? Yes, what did you say?
3 into 10 raised to minus 6.
Okay, let us forget about those numbers. So for the time being, forget about those numbers. So let's focus on this diagram. So let's focus on this diagram, and you tell me what is the total charge inside. So we have learned in the properties of the charges topic that charges follow addition of additive properties of the charges. So total charge is algebraic sum, right?
Yes, sir.
So what would be the total charge inside this sphere?
0.
Yes, absolutely right. So Q minus Q by epsilon naught. So this is C. So what would be flux then? Yes, what would be the flux then? Yeah, so total charge is 0. So flux would be Q enclosed, which is 0 by epsilon naught. So this is 0. So the answer would be 0. Is that clear, guys?
Yes, sir.
Yes, sir.
Yeah, so we don't need to worry about these numbers. So whatever the value they have given, it may have been whatever value. So that would ultimately will give you 0, right? Because the total charge will add up and this would give you 0. So yeah, just quickly note it down. You don't need, yeah, you have only 2 sentences to write. So note it, guys.
Yes, sir.
Yeah. So let me erase this part and let us do the second problem. Two parallel infinite line charges with linear charge density lambda coulomb per meter minus lambda coulomb per meter are placed at a distance 2r in free space. So we have 2 linear charges. One is this, the other one is this. Right, and the distance between them is 2r, but this is lambda and this is minus lambda. Okay, so and they want us to calculate the electric field midway. So electric field at this point. So this is R and this is R. Okay, so let's say that this is E1 and this is 2. Right. So let me ask this to Rabia, that what will be the electric field at this point due to this one, left or right? So this is plus plus plus, this is minus minus minus. Yes, Rabia, I'm calculating the electric field at the midpoint. So this would be due to this one line. So this would be in the right hand side or left hand side, direction of electric field. Yes, Rabia. Right or left?
Left.
Yeah. Okay. So for positive charge, the electric field lines are going away or coming at the positive charges. For positive charge, is it like this or like this? Which one is correct? Going away or coming towards the charge? So for positive charge, this is outgoing, right? And for the negative charge, it is incoming. So this is positive. So the electric field would be yes. Rabi, is that clear?
Yes, sir.
And Aisha, you tell me what would be the direction of the electric field due to this second line linear wire. So what would be right or left at this point? Yes.
Right.
Yeah. So your voice broke in midway. Yeah. What did
So
you
could
say,
you repeat?
Aisha? Yeah, I am asking that for this line charge distribution, what would be the electric field at this point? Will it be right or left?
Right time.
Right, right, because this is negative, so the electric field will come at this linear charge. So this is E2. So you guys can see that E1 and E2 are in the same direction. So the electric field would be simply E1 plus E2. Right. The magnitude would also be E1 plus E2 because they are in the same direction. Let's say if this is I hat, so this is also I hat, so this will add up. Okay, but what is the magnitude of E1? At this point, this is R distance. So what is the magnitude of E1? Rabia. Yes. Yes, Rabia, magnitude of E1. So you have a linear charge distribution. And you just told me what is the electric field due to this linear charge distribution. You have just told me. Yeah. What is the electric field of this linear charge distribution? Rabia.
Lambda 2 pi epsilon naught r
Yeah.
square.
No, not R square, R. So this would be lambda by 2 pi epsilon naught. And what is the distance? R. Right. And E2 is the same distance away from this lambda. So this E2 would be again lambda by 2 pi epsilon naught R. So the total would be lambda by 2 pi epsilon naught R plus lambda by 2 pi epsilon naught. So half, that will give you 1. So pi epsilon naught. This is the electric field. And what is the SI unit of electric field? Newton per coulomb. Right. So which is the answer? This one. You guys please note down this this part. Is that clear, guys?
Yes, sir.
Yeah, please note it down.
Sir, should it be 2 pi?
Yes, should it be?
Shouldn't it be 2 pi?
2 pi. Where? 2 pi.
In the total.
Yeah, so lambda by 2 gives you lambda. Half is how much? 1. Okay, let me write this. So 2 lambda by 2, right? So 2 cancels and E is lambda by 5 epsilon naught. Okay, because lambda by 2 pi epsilon naught, 2 pi epsilon naught. So 2 into lambda by 2 epsilon naught. So 2 cancel. Is that okay, Rabia?
Yes, sir. Got it.
Okay, you guys quickly note it down and then we'll do the next question. So you can see that they ask you simple questions in NEET. So 1919. So yeah, noted, guys.
No, sir, 1 second.
Okay, please note it.
Done, sir.
Aisha, done.
Yes, sir.
Okay, so let us see this next problem. A hollow metal sphere of radius r is uniformly charged. The electric field due to the sphere at a distance r from the center. As r, okay, increases for r less than r decreases as r increases r, right? 0 as r increases for r less than r increases as r increases for r. What is written? Yeah, decreases as r increases r and for r okay, increases as r increases. Yeah. Okay, so this part, who is going to tell? Yeah, Aisha. So you have a hollow metal sphere of radius r, which is uniformly charged. The electric field due to the sphere at a distance r from the center. So we already know the electric field due to hollow sphere. So this is r distance, right? And E inside is how much, Aisha?
0.
0. And E outside is KQ. Let me write it as KQ by R square. Right. So
Yeah.
E inside meaning R is less than R. Right. And E outside meaning R is greater than R. Right.
Yes, sir.
So as you can see that as R increases to R, E is 0. 0 as R increases from R less than R. Right. And decreases as R increases for, so E is 1 over R square. So this is increasing or decreasing. If I increase R, if I increase R, so E will decrease or increase?
Decrease.
Decrease, right? Because it is inversely proportional to R square. So if I increase R, so this will decrease my electric field. Right, Rabia?
Yes, sir.
So this option is correct, right? Yeah. So any doubt in this question, guys?
No, sir.
No, sir.
Yeah. So you guys can see that how tough the questions are, right? So okay. What is the flux through a cube of side of A of if a point charge of Q is at one of its corner, right? So remember, Aisha, this was your
Yes, sir.
homework, but you
I
guys
did it.
didn't send me that. So you say you have sent me the homework.
Yes, sir. I got Q by 8 epsilon.
Oh, yeah. So if you have done the problem then, yeah. So yeah. So Rabia, did you understand that why it would be Q by 8 epsilon naught? You have a charge which is placed at the corner of this cube, right? So
Yes, sir.
we know that. What do we know that? Yeah, we know that the charge or the electric flux inside a closed surface is how much? Yeah, electric field inside a closed surface is how much, Rabia? And flux inside a closed surface is how much?
1 by epsilon naught.
Q by epsilon, right? So we have to make this corner. We have to make this corner inside some surface, right? Inside some surface. So how can we make that? Let's say I have this charge here. So I place one cube here. I place one cube here. I place other cube here. I place other cube here, right? So how many do I have? And then above 3, right? So 1, 2, 3, 4, and above 4. So how many cubes do I have? Yes, Rabia. Did you
8.
understand? 8. So did you understand that part? So how I made this cube at the center or inside some sphere? How I made this cube? So did you understand that part?
Yes, sir.
Yes.
Yes, I understood.
Yeah. So 8 8 cubes give me, or 8 cubes give me how much? Q by epsilon naught. So 1 cube, right, which would be, this would give me Q by 8 epsilon naught. Understood? So the answer would be this. Is that clear, guys?
Yes, sir.
Yeah. So you don't need to note down, because yeah, if you want to note down, you just have to understand this problem. Okay. Yeah. So let us come to this next problem. We have a square surface of side L meter in the plane of a paper. So let's say we have this plane. We have this plane. We have this plane and a uniform electric field acting along the same plane. So the electric field is in the same plane, right? This is along the same plane. Okay. But first, let me ask you this question, that if you have this plane, so what is the direction of the surface area vector? Yeah. What is the direction of the, for this plane, what is the direction of the surface area vector? A. Yes. Rabia. For this plane, what is the direction of the surface area vector? Yes, Rabia. Forgotten? Yeah, am I audible, guys?
Yes, sir, you're audible.
Yeah, so what is the direction of this surface area vector? That would be this, perpendicular to this plane, right? Right,
Yeah.
Rabia? Yeah.
Yes, sir.
So this is whatever surface we have, the direction of the surface area is always normal to this surface, always perpendicular to this surface. Am I correct, Asha?
Yes, sir.
Yeah. So this is the direction of the area vector, right? And you have this electric field. You have this electric field which is in the plane. So your flux would be E dot A, which means that this is EA cos theta. So Aisha, you tell me what is the angle between electric field and the area vector? Yes, Aisha.
60.
60? So you have this electric field which is along this plane. Sorry. So this is the electric field, right? Along this plane, right?
Yes, sir.
And this is my area vector. So what is the angle?
90.
90 degree, right? Rabia, what is the angle? Yes, Rabia, what is the angle?
90 degrees.
So theta is 90 degrees. So this would be 0. So phi would be 0. Is that clear, guys?
Yes, sir.
Yes, sir.
Okay. So yeah. So what would be the answer? This one. So you guys quickly note it down, but we have to just understand these questions. Okay, so just quickly note it down and then we'll do the other problem. So do you guys also note down the question?
No, sir.
So how do you understand that? What is the answer? So what is the question of this answer? So how do you understand the question?
I take screenshots and write
Ah,
down the
then
question number.
yeah, then it's good. Then it's good. And Aisha, what about you? Why?
Same
How do
thing.
you identify the question?
I do
Same.
the same thing.
Okay, noted, guys.
Yes, sir.
Yeah. So let us understand this next question. So we have a hollow cylinder has a charge Q coulomb within it, right? If phi is the electric flux in the unit of voltmeter associated with the curved surface B, the flux linked with the plane surface A in unit of voltmeter with B, right? So oh where is that class? Okay, guys, give me one moment. I need to bring that this cylindrical shape class. Give me one moment, guys. Okay, so sorry about that, guy. I just went to bring this glass, right? So this is somewhat a cylindrical glass, right? Right,
Yes,
guys?
sir.
Yes, sir.
And let's assume that this is open, but let's assume that this is closed somehow, right? This is closed, and this is the curved surface. Okay, guys.
Yes, sir.
And you have you tell me that what would be the total flux. So this is a closed surface, this is a closed surface, and what would be the total flux? Let me write it as total because I have a phi in there. So what would be phi total? Remember, this is a closed surface, so phi total would be how much? Aisha? Yeah. Your voice broke again. So, did you say, what did you say?
Q by epsilon.
Yes, absolutely correct. So, Q by epsilon. Right, Rabia, is that right?
Yes, sir.
And you guys tell me how many surface do I have for this cylindrical surface? How many surfaces do I have?
Three.
Three, right? One is this, the other one is this, and the third one is this curve. So I have this one, this two, and this is third. Right. So phi total would be phi 1 plus phi 2 plus phi 3. Is that correct, guys? Yes.
Yes, sir.
Yeah. So you see that if phi is the flux in unit of voltmeter associated with the curved surface B, so this phi 3 is how much? Phi. This is given, right? And we have to find this phi A, which is this 2. So you guys can tell me that this is the same area as this one. So phi 2 would be equal to phi 1, right? Is
Yes,
that?
sir.
Yes, sir.
Yeah. So this is phi 2 plus phi 2 plus phi equals to Q by epsilon naught. Is that correct, guys?
Yes, sir.
So we have to find this phi 2, which is phi a, right? So this is 2 phi 2, and this would be q by epsilon naught minus phi. So my phi 2 would be how much? 1 by 2 q by epsilon naught minus phi. So is this, do you guys have any doubt in this question? Is this clear, guys?
Yes, sir.
Yeah, so this is the answer. You guys, please note it down, and then we will do the next question.
Done, sir.
Done. Rabia, done.
Just a second, sir.
Just a minute.
Yes, sir.
Yeah, your voice is lagging, Rabia.
Done, sir.
Done. Okay. So let us do the next question. Again, so very difficult question. So this is a similar question that we have done before. So Rabia and Aisha, you guys tell me what would be the answer. We have a square surface of side millimeter in the plane of the paper, right? A uniform electric field also in the plane of the paper is limited only to the lower half of the square surface. The electric flux associated with the surface is, what is phi? Yes. So Rabia and Aisha, you guys find the answer and tell me. Is this, so the total area is how much? This is L square. So half would be L square by 2. So E into A is EL square by 2, right? And yeah, so you guys tell me what is the answer. So Aisha and Rabia, what is your answer?
No, it's 0.
0.
Option C.
So option C. So Rabia and Aisha, yeah, both have said C. So yeah, so I was trying to, yeah, divert you guys from the answer, but yeah, this is 0. Why? Because this is the surface, right? And the electric field is on this surface only. And the direction of the area vector is perpendicular. So E dot A is EA cos 90. So yeah, so E dot A, so EA cos 90, so 0. Absolutely correct, guys. Well done. Okay. So now let us, okay, I don't have many questions to do. So yeah, so let me Okay, so 39th question. A charge Q is located at the center of a Q. The electric flux through any phase. So we have a Q. And the charge is placed at the center. So they want us to calculate the electric flux at one of the phases. So how much would that be, Rabia? Yeah. So how much would that be? Yes, Rabia. Yes, Rabia. We just calculated at the corner. So
Q by 8 epsilon naught.
Q by? Yeah, Q by how many epsilon naught?
8 epsilon naught.
8. So, yeah, we are talking about the phases. We are talking about the one of the phase. One of the phase, this one. So you see that forget about this phase. Forget about this phase for now. Right, forget about this phase. And you have one Q. So you tell me that what is the flux through this cube? What is the flux through this cube? This is a closed surface. This is a closed surface. So what is the flux through this cube? Yes, Rabia. Gauss law, Gauss law.
Q by epsilon naught.
Q by epsilon. Right. So now that we know that the flux through this cube is Q by epsilon. Now what they are asking that what would be the flux through one of the faces, either this one or this one or whatever, this one, either of the faces, right? So how many faces do we have in a cube? This is a cube. Not this is not exactly a cube, but a cuboid. But let's assume that this is a cube. So we have 1, we have 2, we have 3, we have 4, we have 5, and we have 6. 6 faces, right, Rabia?
Yes, sir.
So 6 faces give you how much? Q by epsilon, right? Is that
Yes, sir.
so one phase would give me how much?
Q by 6 epsilon naught.
So did you understand that?
Yes, sir.
Yeah. So Aisha, tell me what is the correct option? Yes, Aisha. Aisha.
Yes, sir, could you repeat?
Yeah. Yeah, Aisha, you tell me what is the correct option here. We have these 4 options. So what is the correct option? You know that the
D.
answer is yeah, D.
Yes.
Yeah, because 4 pi cancel and we have Q by 6 epsilon. So this is the correct. So understood, Rabia?
Yes, sir.
Yeah. So just remember that whenever we want to calculate the flux, we used to have that relation of closed surface. So we make the closed surface and we put it to Q by epsilon, and then we break all those surfaces. Okay. Similarly,
Yes.
so this was the only logic that we were using. So in this case also, and in this case also, and all in all the questions. So we applied that logic only, right? Okay, so Rabia, you quickly note down this problem, and yeah, so Aisha has already done this question in the class. So, and you have also done this in your class, right? So maybe you have forgotten. Okay, just quickly note it down, Rabia, and then we'll do this 40th problem.
Done, sir.
Yes, so, okay, this is the same question as this 39 one. So we have this, a charge q microcoulomb is placed at the center of a cube of a side 0.1 meter, then the electric flux diverging from each face of the cube is, right? So that would be how much? We know that it would be pi one face would be q by 6 epsilon. And this q is microcoulomb. So q into 10 to the power. How much is microcoulomb? Yes. How much is micro?
10 raised to minus 6.
Yeah, -6, right?
Yes, sir.
And this would be 6 epsilon naught. So this would be the answer. So this option. So you guys quickly note down this problem. Yeah, so note it, right?
Yes, sir. Done.
Okay, very, very tough question. So a hollow insulated conducting sphere is given a positive charge of 10 microcoulomb. What will be the electric field at the center of the sphere if its radius is 2 meters? So what is the answer, guys? We have this conducting sphere and it is given 10 microcoulomb charge. So we have to find the electric field at the center. So what would be electric field at the center? Aisha?
0.
0. Right, so this one. Okay, so these are very tough. I have only 2 questions and I have how many? I have half an hour more. So yeah, what should we do? So then you guys calculate the 44th question.
Now, what is NDP?
Yes?
What is NDP?
Normal temperature and pressure. Normal temperature. So you have this atmospheric ATP, atmospheric temperature and pressure, and then you have this NTP, normal temperature and pressure. Yes. So what did you get, guys?
Sir, is it option A?
Yeah, is it? Yeah, is it?
Option A, like I'm getting 3 into 10 raised to minus 4.
Yeah, so we know that how much is, so we know that E is how much? KQ by R square. So this is at the surface, right? So this is E is given 3 into 10 to the power 6, and we have this 3, and then we have this 3 into 3 divided by 9 into 10 to the power minus 9. Oh, minus not my 9, 9. Right, this is, so how much we would get? 3 cancels this, and 9 is minus 3. So Q is 3 into minus 3 Coulomb. So are you guys getting this value? Yes. Is
So
this
how
the
did
value that you guys? Yeah.
so how did we get the value of 9 into 10 raised to the power 9?
So what is K? What is the value of K? So this is K is 1 by 4 pi epsilon, right? And this equals 9 into 10 to the power 9. So you have to remember this value. So in calculation, this will come again and again. You have to remember this value. Right,
Then
Rabia, do you remember now?
that, yeah, so but then why did we take another 3? There's like only 1 3 given in the question, right?
Yeah, so why, what have this, what have this guy has done to you? So you have this R square. So R is 3. So 3 square, 3 into 3, right?
Right, so
So don't forget about this poor guy, radius. This guy didn't do anything to you, right? Okay, so yeah, Aisha, clear?
Yes, sir.
Yeah, so this option is correct. Okay, so what should I do? I have one question and I have 20 minutes. So what I will do is that I will end the class early, right? Okay, so do I have any tough question? Let me see. So I can take it from here. No, these question I cannot ask. These question I cannot ask. What should I? Okay. So I don't have. Okay, so that will be the last one. Yeah. So let me see if I have any more question from. Because we have 15 minutes, right, guys? Oh, so you guys can calculate. Two spherical conductors A and B of radii are separated by distance 5 centimeter. If the spheres are connected by conducting wire, then in equilibrium condition, the ratio of magnitude of the electric field at the surface of sphere will be. Right, so you guys calculate. So are uniformly charged. Yes. So two spheres are connected and you have to calculate electric field at the surface of sphere A and surface of sphere B. Right. So you guys calculate and tell me the answer. And let me see if I can find more problems on it. So yeah, are you guys doing this problem?
Yes, sir.
Yes, sir.
Yeah, please do this problem and then yes, what is the value did you guys? Oh, you guys take your time because we have ample amount of time. So electric dipole. Hmm.
Sir, is it option C?
Option C. So Rabia's answer is option C. And Aisha.
C.
Aisha, you also got. So how did you guys get option C? E is how much? At the surface we are calculating. So let's say E1 would be KQ by R1 square. E2 would be KQ by R2 square. So E1 by E2 would be KQ1 R1 square, KQ2 R2 square. QQ cancel and E1 by E2 is R2 square, R1 square. Is that correct, guys? This is A and this is B. So you will get E1, what is the radius of, so this is 1 millimeter. Let's say this is A, this is B. So this is 1 millimeter, which means that millimeter is how much? 10 to the power minus 3, 10 to the power minus 3. And this is 2 millimeter. So 2 into minus 3 minus 3. So how much you will get, guys? Yeah,
4:1.
4:1. So how did you guys get 2:1?
I did not convert
Yes.
it into meter.
Yeah, so we have a square, right? So that is how it
I
will
just
be.
did R2. I did not square it.
Okay, okay, good. Okay, so then yeah, then I don't have any question left, so we can end the class. Right, because all the question are for yeah, we have different kind of distributions. So
Sir,
yes,
in the NEET exam, will they ask about laws?
no, they will not ask about this. Okay, Gauss law. They will So in the entrance or in the competitive exam, that is about only the application of whatever you have learned, right? Only the application they will ask. They will not ask about what is this definition and right.
Okay,
So
sir.
they will ask about the application of those concepts that you have learned. Okay.
Okay, sir.
Yeah.
Thank you.
But yeah, but they can ask something like this, that how the electric field varies with respect to this R. So E1 over R square. So these kind of questions they can ask. Just you, so as you saw in this problem, in the case of this dipole problem, right? So in these kind of question, you saw that how they will ask. So how this electric field varies, right? So these kind of question they can ask. Variation kind of questions. Right, guys?
Yes, sir.